Good afternoon, everyone. So this will be the second session with respect to our NEET 2024. We have already started magnetism, right? So part one of the magnetism is done for the NEET classes, right? We'll be discussing the part two of the magnetism, and we'll be discussing some of the important questions in this session as well, right? So we'll be starting with the question number one. The question number one is that a hollow cylindrical wire carries a current 5 amperes, having inner and outer radii R into a respectively. Find the magnetic field at a point which is 3r by 2 distance away from its axis, right? So in this question, we have a magnetic wire. We have a cylindrical wire, right? This is the cylindrical wire. And this cylindrical wire has two radius, right? It's a hollow cylindrical wire, right? It will have two radius, right? So let's suppose this is inner circular portion and this is the outer circular portion, right? The radius of the inner circular portion is given as r. The radius of the outer circular portion is given as 2r, right? 2r. And the current flowing through this cross section is given as 5 amperes, right? So this will be the cross section, right? This will be the cross section through which the current of 5 amperes is flowing, right? Through the cylinder. The current is given as I equal to 5 amperes, right? 5 ampere of the current is flowing through it, right? Now we have to find a magnetic field at a point which is 3r by 2 distance away from its axis, right? There's a point in between the two circles, right? There's a point in between the two circles, or we can say there's a point in this region, right? This is the point P, right? At this point P, we have to find the magnetic field, right? At this point P, we have to find the magnetic field. What we'll do is that we will just draw the Amperian loop at this point, right? We'll construct an Amperian loop at this point. So this will be the Amperian loop. So this is the Amperian loop here, right? Let's suppose the radius of this Amperian loop is small r. So small r is the radius of this Amperian loop. Now, the magnetic field at this point P will be given by the Ampere's second law. That's integral of P dot dl will be equal to mu naught I enclosed, right? Now, I enclosed will be the current enclosed by this Amperian loop, right? We know at each and every point on the Amperian loop, the magnetic field is a constant in magnitude, right? So, in the direction of the P vector and the dl vector is same, right? So angle between them is 0. That will be theta is equal to 0 degree, or cos of 0 will be equal to 1, right? So we're left with this integral as it will be integral of P dl only, right? That's equal to mu naught I enclosed. The P is a constant on the Amperian loop. The magnitude of the magnetic field on the Amperian loop is constant. We'll take it outside the integral. We'll be left with integral of dl. That will be equal to mu naught I enclosed, right? Mu naught I enclosed. So the value of P here will be equal to, that will be mu naught I enclosed upon the 2 pi r, right? Upon 2 pi r. 2 pi r, right? Now we have to calculate the value of this enclosed current within this Amperian loop, right? We know the current is actually flowing flowing in this portion of this cylinder, right? Of this hollow cylinder. Now to calculate the current enclosed by the Amperian loop, right? The current density for this cylindrical wire will be a constant, right? That J will be equal to current I upon the area. And this is the portion through which the current is actually flowing. And this area will be equal to the area of the larger circle minus the area of the smaller circle, right? That will be 4 pi r square minus pi r square, right? Now the current I is given here as, that's 5 amperes. That will be 5 upon 3 pi r square. So this is the current density, and the current density has to be a constant, right? That will be 5 upon 3 pi r square. It has to be a constant. And the current density through this Amperian loop will be, let's suppose I is the enclosed current, right? By this Amperian loop, right? Divided by the circular portion of this area, right? Circular portion of this Amperian loop. And we know that only in this portion of Amperian loop there will be current, right? The current density will be only associated with this portion of this Amperian loop, right? We'll just write it as it has to be equal to pi small r square minus pi r square, right? So from here pi and pi will get cancelled, right? Now the value of r is given as, that's 3r upon 2, right? We'll be left with 5 upon 3 r square, right? That will be I enclosed. The value of small r is 3r upon 2. So it will be 9r square upon 4, right, minus r square. So the I enclosed will be here equal to, that will be I enclosed upon 5r square, and there will be 4 in the numerator, right? So r square and r square will get cancelled. Will be left with I enclosed as, that will be equal to 25 upon 12 amperes, right? This is the enclosed current within this ampere loop, right? We'll substitute this value of current in this equation to get the magnetic field. That will be mu naught I enclosed is 25 upon 12, right? Divided by 2 pi r. The value of r is given as 3r by 2, right? 3r by 2. From here, 2 and 2 will get cancelled, right? So it will be a mu naught, 25 mu naught, right, upon 36 pi into r. So this will be the value of the magnetic field at a distance of 3r by 2 from the center of this hollow cylindrical wire, right? Let's move to the next question. The question is about a long straight wire, right? A long straight wire. We have been given a long straight wire of radius 3 mm, carries a constant current distributed over a cross section perpendicular to the axis of the wire. The current density is 50 amperes per meter square. The magnitude of the current, the magnitude of the magnetic field at 1.5 mm from the axis of the wire and 4 mm from the axis of the wire. Now you can see here radius of this wire is 3 mm, and the 4 mm point from the axis of the wire will lie actually outside this long straight wire, and 1.5 mm distance from the axis will lie within the wire, right? So we know that outside the cylinder or outside the wire, the magnetic field is actually, it will be mu naught I upon 2 pi r, right? We know the magnetic field for outside wire is inversely proportional to the distance r. Similarly, the magnetic field inside the wire is nothing. It is mu naught. It will be mu naught I multiplied by r upon 2 pi r square, right? Here r, capital R, is the radius of this cylindrical wire, right? I can see here we can just substitute the values here, right, to get the magnetic field. Now the current density here has been given, right? The current density will be nothing, that is J is equal to I upon pi r square. This is the current density, right? It's a uniform current density, right? Now we can replace I upon pi r square here in this equation by J. That will be mu naught J into R upon 2, right? This will be the magnetic field inside, right? The value of the current density is given as 50, right? It will be, we'll substitute the value of J here, that's given as 50 amperes per meter square, right? So it will be 50 upon 2 mu naught R. Now the value of R for the inside point is given as 1.5 mm, right? 1.5. We can write it as 1.5 into 10 to the power minus 3, right? So it will be 25 multiplied by 1.5 to mu naught multiplied by 10 to the power minus 3, right? So from here, the value of the magnetic field will be 25 into 1.5, and substitute the value of mu naught, that's 4 pi into 10 to the power minus 7, that will be 10 to the power minus 10. So this much will be the magnetic field inside the wire, right? Similarly, for outside region, the magnetic field will be, if we multiply here with r square and divide also by r square, right? We can replace this equation as mu naught r square into J upon 2r, right? So this will be the magnetic field in terms of the current density, right? Now, once again, you can substitute the value of current density here. The value of J is given as 50, right? And the R, capital R, is the radius of this wire, that's given as 3 mm, right? That's given as 3 mm. So we can write it as 3 into 10 to the power minus 3 whole square, right, upon 2r, right? 2r. Now the value of r here is, it's for a point which lies outside the cylinder, that's 4 mm. That will be 4 into 10 to the power minus 3, right? So this will be the magnetic field due to this current carrying straight wire, right? For the outside point as well as for the point lying inside the wire, right? So this is how we can find the magnetic fields, right? Due to two different situations, right? Now, the question number 3 is that a closely wound solenoid 80 centimeter long. It means that we have to talk about the magnetic field due to a solenoid. Now, let's suppose we have a long solenoid, right? Long solenoid. And let's suppose the length of the solenoid is L, and there are N turns in this solenoid, right? N turns in this solenoid. The magnetic field along the axis of the solenoid will be a uniform magnetic field, right? It will be a uniform magnetic field, and uniform magnetic field lines are actually represented by the straight lines parallel to each other with equal distances between the two magnetic field lines. So let's suppose L is the length of the cylinder, length of the solenoid, N are the number of turns. Then the number of turns, capital N per unit length, that will be N upon L, right? The magnetic field here along the axis of this solenoid, that is a constant magnetic field, that will be mu naught Ni, right? Mu naught Ni. Here N is nothing; it's a number of turns per unit length, right? Number of turns per unit length. Now let's replace this with N turns and small n with the number of turns per unit length, right? So it will be number of turns per unit length. So this will be the magnetic field due to a solenoid. Now the question is that a closely wound solenoid 80 centimeter long has 5 layers of winding. There are 5 layers of winding of 400 turns each, right? So the length of the solenoid is given as 80 centimeter, right? There are 5 such layers, and for each layer we have winding of 400 turns, right? 400 turns. It means that number of turns per unit length will be, it will be 400 upon 0.8, right? That will be nothing, that will be equal to 500 turns per unit length, right? This will be the 500, right? The number of turns per unit length will be 500, right? The magnetic field, because of all these windings, will be, since there are 5 layers, we'll multiply it by 5, right? Multiplied by the mu naught, right? Number of turns per unit length, that's 500, and the current through each of these winding is 8 amperes. We'll multiply here with the 8, right? So the magnetic field here will be, so it will be 40 multiplied by mu naught into 500, right? So it has to be equal to 20,000, right? 20,000 multiplied by mu naught. Now the value of mu naught is nothing. You can write here it as 2 into 10 to the power 4, right? Multiplied by 4 pi into 10 to the power minus 7. That's the value of mu naught, right? So we'll be having 8 pi into 10 to the power minus 3 Tesla, right? This will be the magnitude of the magnetic field along the axis of this solenoid, right? So 8 pi multiplied by 10 to the power minus 3 Tesla. So this much of magnetic field will be there between the or along the axis of the solenoid, right? Now let's discuss the question number 4, right? Talking about the question number 4, from the path followed, identify nature of the charge, right? You can see here, whenever a charge particle enters a magnetic field or it enters a region containing the magnetic field, right? Then in that region, there's a possibility that charge may experience a magnetic force, right? And the magnetic force experienced by the charge is given by the equation that F vector will be equal to F magnetic force will be equal to Q times V cross V, right? It's a cross product between magnetic field and velocity vector, right? Now, the particle you can see here, let's look at this particle 2. This particle 2 does not show any deflection at all. It means that the particle, since there is only force, that's the magnetic force, that the only force that can be there is the magnetic force, neglecting the gravity and all, right? So we are neglecting the gravity. We are just assuming that gravity in this region is 0, right? So here in this region, the only force that can act is the magnetic force, right? So the for the particle second, there is no deflection at all. It means that the net magnetic force on this particle second has to be 0, right? So let's put this F equal to 0 in this equation, right? Now there are two possibilities for this magnetic force to be 0. Either the charge on this particle is 0, or we can say the cross product between the velocity vector and the magnetic field vector will be equal to 0, right? Now let's see whether the cross product of velocity vector and the magnetic field vector is 0 or not, right? So you can see here, in this situation, you can see here, this is the direction of velocity vector, right? And magnetic field is into the plane of this paper, right? You can see here the magnetic field vector and the velocity vector are at 90 degree to each other, right? If the magnetic field vector and the velocity vector are at 90 degree in each other, right? So it means in the case second, the V cross B is not a 0, it's a non-zero quantity, right? V cross B is a non-zero quantity. It means that the only possibility here is that the charge of this particle must be a 0 charge, right? It means that this second particle will be a neutral particle, right? The second particle will be a neutral particle, right? So the charge on the second particle will be 0, right? Q will be equal to 0. It will be a neutral particle, right? Now, talking about the question, particle 1, right? You can see here the particle is experiencing some force because there is some deflection shown by this particle, right? And the deflection is along this curve, right? It means that the magnetic force must be acting along this direction, right? On this particle, right? Now you can see here you can see here, if we calculate the direction of the magnetic force, that will be given by the V cross B, right? So V cross B is also along this direction, right? So V cross B is along the direction of the magnetic force. It means that the charge on this particle has to be a positive charge, right? It has to be a positive charge, right? So we can say that the particle first is nothing, it's of positive charge, right? The charge on this particle first is positive charge, right? Now, similarly, we have the third particle here, talking about the third particle, right? The deflection shown by this third particle is along this direction, right? So it means that magnetic force has to be along this direction, but the direction of the V cross B is along this direction. This is the direction of the V cross B, right? So it means that the direct net direction of the that force will be in the downward direction only if the charge on this particle is a negative charge, right? So the third particle will once again be a charged particle, but the charge on this third particle will be a negative charge, right? It will be a negative charge. So the charge on the third particle will be a negative charge. So for a second particle is a neutral particle, right? And the first particle is a positively charged particle, and the third particle is a negatively charged particle, right? Now let's discuss question number 5, right? A proton, neutron, and an alpha particle are moving perpendicular to magnetic field, and find the ratio of their radii, right? We know that whenever a charged particle is moving perpendicular to the magnetic field, then the path followed by that charged particle, once the magnetic force acts on it, is a circular path, right? The charged particle will move in a circular path, and the maximum force acting on that charged particle will be QVB. That will be equal to the centripetal force. That will be mv square upon r, right? So from here, m and v and v will get cancelled, right? V and V will get cancelled. We can say that the radius of the circular path followed here will be mv upon qb, right? It will be mv upon qb, or we can write it as momentum upon the charge multiplied by the magnetic field, right? Now you can see here, if the two particles are moving with the same speed, it means this v is constant here. Then at that time, the ratio or the radius will be proportional to radius has to be proportional to r will be proportional to m m upon qb, right? It will be proportional to m upon qb. Since the magnetic field is also constant, so radius will be proportional to m and q, right? So with same speed, the radius will be proportional to m by q. With same momentum, the radius will be proportional to uh, it will be inversely proportional to the charge, right? Since the magnetic field is also constant, momentum is also same, right? So R will be inversely proportional to the charge. Now talking about the kinetic energy. Now we can write this radius in terms of the kinetic energy as well. We know the relation between the kinetic energy and momentum is that P square upon 2m, we can write it as equal to P square upon 2m, we can write it equal to kinetic energy, right? Now the momentum here will be nothing, it will be under root of 2m times kinetic energy upon the charge multiplied by the magnetic field, right? Now, if the two charged particles move with the same kinetic energy, then at that time the radius of the circular path will be proportional to r will be proportional to under root of m upon q, right? So this will be the proportionality in that case. Now, case fourth, right? Talking about the case fourth. Now, if we apply some electric field, or we apply some potential difference for the charge, right? If a charge particle is moving against the potential difference, right? Then we can say that then the kinetic energy attained by that particle will depend upon the potential difference, right? Or we can say the kinetic energy of this particle will be nothing. It will be a charge multiplied by the accelerating potential of that provided potential, right? So charge multiplied by the provided accelerating potential will give us the net kinetic energy of this charge particle, right? Now we can replace this kinetic energy with Q multiplied by this accelerating potential. So R, we can write it as under root of 2m q multiplied by v upon qb, right? Or we can rewrite it as under root of 2mv, right? So it will be under root of 2mv upon q multiplied by v, right? Where v here is the accelerating potential, right? V is equal to accelerating potential, right? V is nothing, it's the accelerating potential, right? Now we can see here clearly for the fourth case here, the radius will be proportional to the accelerating potential is same. It means that it will only depend upon the charge, right? And mass, right? So the radius will be proportional to under root of m upon q, right? Under root of m upon q. So this will be the proportionality, or this will be the dependence of the radius. Now, for any two particles with the given condition, you can find the radius ratio of the radii if they are moving with different conditions, with same speed, with same momentum, with same kinetic energy, through same accelerating potential, right? So this is how we can do this question, right? Now let's move on to the question number 6. A charged particle enters in transverse magnetic field as shown in figure. Then find the deviation, right? Then find the deviation or time for which particle remains in magnetic field. Displacement of a particle when particle emerges out, right? Now you can see here when charge enters this magnetic field, right? Charge enters in this magnetic field, and because of this velocity vector along this direction, this particle will follow a once it enters the magnetic field region, it will follow a circular path like this, right? This will be the path followed by this charged particle, right? This will be the path followed by this charged particle, and it will leave the magnetic field region like this, right? It will leave the magnetic field region like this. So here the particle will leave the magnetic field region, right? Now you can see here the region is not the whole of the region is not, or we can say the dimensions of the region in which the magnetic field is present is not sufficient for this charged particle to complete a circle, right? So it will leave this magnetic field, right? So it will stay for in this magnetic field region for a very short time, right? Then it will leave this magnetic field region, right? Now the question is that how we can find the magnetic deviation angle and the time for which the particle remains within this magnetic field, right? Now you can see here, if this angle here, let's suppose it enters at an angle of theta, then this angle also has to be equal to theta, right? So the net deviation will be nothing. It will be equal to the angle at which the particle enters the magnetic field, that's theta. Then the deviation will be equal to twice theta, right? It has to be equal to twice theta, right? The time t that the particle spends in this magnetic field, that's given by twice theta, right, upon 2 pi, right, multiplied by the time period for the complete circle, right? So for a complete circle, the particle subtends an angle of 2 pi or 360 degree with respect to the center of that circle, right? So it means that if t time is spent by this charged particle in this magnetic field, then the time spent will be actually equal to, it will be t upon pi multiplied by the theta, right? Now theta is the angle at which this particle will enter the magnetic field, right? I can see here it's given theta here is given as 45 degree, and we know the time period for the charged particle we can calculate as if the particle moves in a circular path, the time period will be 2 pi r upon the velocity v, right? And the value of r, we know it's nothing, it's equal to mv upon qb, right? It will be mv upon qb, right? And v. So v and v will get cancelled, right? It will be 2 pi m upon qb. You can see here the time period only depends on the charge, magnetic field, and the mass of the charged particle, right? So the time spent in the magnetic field region will be nothing. It will be 2 pi m upon pi multiplied by qb, right? So pi and pi will get cancelled. So this will be the time spent in the magnetic field region. That's 2m theta upon qb. So this is the time spent by the charged particle in a magnetic field region. It's a very important question, right? Time spent by the charged particle in a magnetic field, right? Now, displacement of particle when particle emerges out, right? The displacement of this particle from point here to here is nothing. It will be the initial point is A and the final point is B, right? I can see here, if we draw a perpendicular to this point here, right? Perpendicular to this point and the perpendicular at this point as well, right? These perpendiculars will actually form the radius of the circle, right? We know velocity vector is tangential here, right? Velocity vector is tangential here, and the radius of the circle is perpendicular to the tangent, right? So it means that this from here to here it will be r, and it will also be equal to r, right? So if this is theta, then this has to be theta, and this has to be theta, right? Now we can resolve these two radius into two components. One component will be along this direction, right? It will be r sine theta, right? And for this radius also, the component along this direction will also be r sine theta, right? R sine theta. It means from here to here, the net displacement will be given by the magnitude of these two vectors, right? So the net displacement, delta S displacement is nothing. That will be 2r sine of theta, right? 2r sine of theta. So this is the net displacement of this particle once it emerges out from the magnetic field, right? 2r sine theta will be the net displacement for this charged particle, right? Now let's move on to the question number 7, right? The question number 7 says that a particle of mass m and charge q is projected into a region having perpendicular magnetic field V of width d. Find the angle of deviation q of the particle as it comes out of the magnetic field. We know that the angle of deviation is nothing. Angle of deviation is nothing. Angle of deviation will be nothing. It will be twice of theta, right? Theta is the angle at which the charge particle will enter the magnetic field. So twice that of angle will be the angle of deviation, right? Now let's suppose this is the magnetic field region, right? This is the magnetic field region, right? If this is the region of the magnetic field, and if the charge particle enters perpendicular to this interface, right, at an angle of 90 degree like this, the charge particle enters like this at an angle of 90 degree in this magnetic field region, right? Then the deviation, this charge particle will follow a circular path, right? Because of the magnetic force, and the charge particle will leave this region like this, right? It will make a semicircle here, right? So if this is a 90 degree, it enters at an angle of 90 degree, right? And it leaves at an angle of 90 degree. Now you can see the angle between the initial velocity vector and the final velocity vector is actually 180 degree. So the deviation here will be nothing. That will be equal to 180 degree, right? So the deviation depends upon the angle at which actually the charge particle enters the magnetic field, right? Twice that of angle will be the net deviation for the charge particle, right? Now let's move on to the question number uh, 8, right? A proton accelerated by a potential difference 500 kilovolts moves through a transverse magnetic field of 0.51 Tesla as shown in figure. The angle theta through which the proton deviates from the initial direction of its motion is, right? We have to find the angle theta, right? But we can see here in this question there's a figure missing in this question, right? So this question we will be discussing in the next session, right? Again, because the figure of this question is missing here, right? So we'll be discussing in the next session again. So let's move on to the question number 9, right? A charge particle projected with velocity vector 3 I cap plus 4 j cap in external magnetic field, right? Where the magnetic field is given as 6 Tesla along I cap direction. It means it's along positive x-axis, right? Now we have to find the radius of the circular path followed by this charge particle, pitch of this path, uh, radius of the circular path and pitch of this particle. We'll discuss this, what is pitch, right, and the time period as well, right? Now, let's suppose that if we project a particle at an angle of theta, right, at an angle of theta with respect to the horizontal or with respect to the magnetic field, right? With respect to the magnetic field. There are two components of this velocity vector. One is the v sine theta, and another component is parallel to the magnetic field. That's the v cos theta, right? And because of the component which is perpendicular to the magnetic field, the force acts on this charge particle, right? And because of this, that magnetic force, the charge particle tends to move in a circular path, right? But apart from the vertical force, magnetic force, there is also a horizontal component of the velocity for this charge particle, right? So because of the magnetic force, the charge particle will try to move in a circular path, right? It will try to move in a circular path. But because of the horizontal component of this force, right? Horizontal component of this velocity vector, right? The charge particle will also drift along the horizontal direction. It will also drift towards the right. So in that case, the net direction or the net path of this charge particle will be a helical path, right? It will be a helix, right? It means the charge particle will move like on a helical path, right? Or we can say the trajectory of this charge particle will be helix, right? In that case, it will be the trajectory will be helix, right? So once again, the time period for this circular path, right? For the circular path, let's suppose for the circular path that charge particle will follow, right? Apart from the horizontal shift, the time period of this circular path will depend upon the it will only depend upon the perpendicular component of the velocity, right? The time period will only depend upon the vertical component of the velocity. That will be equal to 2 pi r upon uh, now let's first calculate the radius of the circular path, right? The radius of the circular path will be nothing. It will be mv perpendicular upon qb, right? So it will depend upon the perpendicular component of the velocity vector. The component of the velocity vector which is perpendicular to the magnetic field will decide actually the radius of the circular path, right? So you can see here the magnetic field is along x direction. That's given as 6 t I cap, right? 6 Tesla I cap, right? Velocity vector which is perpendicular, the component of the velocity which is perpendicular to the magnetic field will be the J component of this velocity vector, right? So the V perpendicular has the magnitude equal to 4, right? So the radius of the circular path will be nothing, it will be 4m upon qb, right? The magnetic field is given as 6, so it will be 6 here. So it will be 2m upon 3q, right? This is the radius of the circular path followed by this charged particle, right? Now let's talk about the time period, right? The time period of the circular path will be nothing, it will be given by 2 pi r upon the velocity v perpendicular component, right? It will be v perpendicular, right? Now 2 pi r, we can write r as mv perpendicular upon qb v perpendicular. It means that once again the time period is a constant here, that is 2 pi m upon qb, right? It does not change upon changing the angle between the velocity vector and the velocity vector and the magnetic field. It means that the time period is independent of the magnitude of the velocity, right? The time period here will be 2 pi m upon qb. The value of q is okay, it will be q into b multiplied by 6, so it will be equal to pi m upon 3q, right? Pi m upon 3q will be the net time period. This will be the time period of this charged particle, right? Now, apart from this circular path, the particle will also shift along the horizontal direction. Now, the question is that what is this pitch? The pitch is nothing, it's the shift in this shift for this charged particle along the horizontal direction, right? In one complete time period, right? That's what we call as the pitch of this helix, right? And that pitch will be nothing. Let's suppose x is the shift, that will be the time period t multiplied with the horizontal component of this velocity, that will be v cos theta, right? Now the time period here is given as now talking about the uh, angle between you can see here angle between velocity vector and the magnetic field vector. We can find that using the dot product between them, right? So t v cos theta is actually the component along magnetic field direction, or we can say we can just dot velocity vector with the unit vector of the magnetic field, right? The unit vector of the magnetic field, it means that if we just dot velocity vector with velocity vector with the velocity vector with magnetic field, right? Or we can say that if we dot the velocity vector with I cap, we will get the component along magnetic field vector, right? So it will be t v cos theta. The value of t is pi m upon 3q, right? Pi m upon 3q multiplied by v cos theta. So v cos theta. So v cos theta is nothing. We can write this v cos theta equal to, it will be v vector dotted with I cap, right? So this is the v cos theta, right? Now v vector dotted with I cap will be nothing. It will be 3, right? It will be equal to 3, right? It will be equal to 3. So 3 will be the magnitude of this v cos theta. So it will be equal to uh, 3 and 3 will get cancelled. We'll be left with pi m upon q, right? This is the horizontal shift, right? This is the horizontal shift for this charged particle, right? It will follow a path of helix, right? The radius of the circular path will depend upon the perpendicular component of the velocity with respect to the magnetic field, right? The pitch, once again, is nothing. It's the horizontal shift for this charged particle in one complete time period, right? And the time period, we know that it will be independent of the velocity, magnitude of the velocity vector, right? Now, let's move on to the question number 10, right? The question number 10 is that a particle moving with velocity v, right? The particle is moving with velocity v as shown in the figure, right? The particle is moving with a velocity v as shown in the figure, and then the path of trajectory, right? Then the path of trajectory, and also find the speed, effect on the speed, right? We have to comment on the path or the trajectory of this charged particle as well as the effect on the speed, right? Now let's discuss it a bit in detail, right? Now there are two fields, right? Apart from the magnetic field, there is also electric field, and because of the presence of the electrostatic field, there will be electrostatic force acting on this charged particle. And we know that whenever in a region the electrostatic field is present, then the force in that charged particle will be nothing. That will be Q multiplied by E. And the direction of that magnetic electrostatic force will be along the direction of the electric field vector if the charge is a positive charge, right? Now let's suppose that this charged particle is actually a positively charged particle, right? Let's first suppose that this charged particle is a positively charged particle, right? Now you can see here the velocity vector is along the magnetic field vector. We can say that V cross B here will be equal to 0. If V cross B here is equal to 0, there will be no magnetic force at all. So the magnetic force on this charged particle will be 0 in this case, right? So even if this charged particle is a negatively charged particle, in that case, in that case also the magnetic force on this charged particle will be equal to 0, right? Now the only force here on this charged particle will be the electrostatic force, right? Only force on this charged particle will be the electrostatic force, and that will be a charge multiplied with the electric field, right? Now since initially the angle, you can see clearly the angle between the electric field vector and the velocity vector is 0 degree, it means that the electrostatic force will be along the direction of the velocity vector if it is a positively charged particle, right? And initially the particle was moving along the same direction as that of the electric field vector. It means the force will also be along the velocity vector. It means that the particle will not change its path. It will continuously move along the same path. And initially the path of this particle was a straight line path because it was having a constant velocity vector. Now again, with the given conditions, the particle will once again have the same path, that will be straight line, right? For the positively charged particle, the path will be positively charged particle, the path will be a straight line path, right? It will be a straight line, right? It will be a straight line, right? And what about the effect on the speed? Now you can see here the velocity vector is along the direction of the force. If velocity vector is along the direction of the force, then the speed is going to increase with increase in speed, right? With increase in speed, the speed will increase continuously, right? Now let's suppose if this charged particle is not a positively charged particle, let's suppose it's a negatively charged particle, right? If it's a negatively charged particle, then in that case electrostatic force will be opposite to the direction of what we call as the velocity vector, right? Now once again here, since the velocity vector is anti-parallel to the force here, right? The speed of this particle will actually decrease, right? The speed of this particle will first decrease, then increase, right? The speed of particle will first decrease, then increase, right? And then increase in the opposite direction, right? And then increase, right? The path of this particle will be like a straight line, right? Like this. And somewhere here, the particle will stop its motion, right? It will come at rest since electrostatic force is acting on this particle, and it will move in the reverse direction, right? It will move in the backward direction again with the increase in speed. So first, for the negatively charged particle, the speed of the negatively charged particle will decrease first, and then the speed of this negatively charged particle is going to increase, right? So this is how the path will be same. The path will be once again a straight line for both the particles, whether it's a positively charged, whether it's a negatively charged, right? In case the angle between the electrostatic force and the velocity vector is, let's suppose, theta, right? Let's suppose that this is the velocity vector, right? And this is the magnetic field vector, right? But the electric field vector is at some angle theta, right? Theta, right? Then in that case, for both positively charged particle and negatively charged particle, the path of this particle would have been a parabolic path, right? It will be a parabola, right? The path of this charged particle will be a parabola, right? So if angle between the electric field vector and the velocity vector is 0 or 180 degree, then in that case the path will be a straight line. If angle between the electric field vector, right? Electric field vector and the velocity vector is non-zero or apart from 0 and 180 degree, or we can say the electric field vector and velocity vector are neither parallel nor anti-parallel, in that case the path of that particle will be a parabolic path, right? It will be a parabola, right? So this is how we can find the trajectory and comment on the speeds of the particle, right? Provided the magnetic force is 0, right? If the magnetic force also comes into play, then we have to look at the two equations together to determine the net path. It will be decided by the net force acting on this charged particle. The net force acting on this charged particle will decide the path of this charged particle, right? So this is how we can comment on the trajectory of the charged particle, right? Now let's move on to the question number 11, right? The question number 11 is that a particle having a charge plus 5 coulomb moves with velocity vector given as 3 j cap in an electromagnetic field. So it means that in this region both electrostatic field as well as magnetic field is present. So there can be both forces, magnetic force as well as electrostatic forces. Then find net electromagnetic force on the particle. Let's suppose in some region both the magnetic field as well as the electrostatic field is present. Then the net field will be nothing. Net force will be charge multiplied by the electric field and charge uh, cross protected with V cross B, 2V cross B with the magnetic force, or we can say it will be nothing. It will be net force will be the net electrostatic force plus the net magnetic force, right? This will be the net resultant force vector of this charge particle, right? I can see here the electric field vector is given along j cap direction. We can write it as the charge of 5 coulomb, right? It will be multiplied by 3 j cap, right? And the charge is 5 coulomb multiplied by. So we have to find out the dot product between what is this V? The V is actually the velocity vector, right? E is actually the electric field vector. That's actually along a k cap direction. So it will be twice k cap, right? Twice k cap. And V is given as 3j cap, right? Crossed with magnetic field, right? Now the value of the magnetic field is 3I cap plus 2j cap, right? We'll find out the dot product, cross product between the velocity vector and the magnetic field vector, right? You know this cyclicity of this what we call as uh, unit vectors, right? So j cross I will be nothing, right? J cross I here will be nothing. It will be minus k cap, right? And j cross j will be a 0, right? So it will be 10 k cap, right? It will be a 10 k cap, right? Plus 5 will be here, right? It will be j cross k. It will be minus 3 k cap, right? Minus 9 k cap, not 3. Minus 9 k cap, right? Minus 9 k cap, and be left with 10 k cap minus 45 k cap, right? So the net force is along k cap direction minus k cap direction, or we can say the negative z axis, right? So this is the net force vector or net electrostatic force, net electromagnetic force on this charged particle, right? Now let's move on to the question, right? Find force on given wire in magnetic field, right? The force on a current carrying wire in a magnetic field due to the external magnetic field is nothing. It's always equal to, that's given as integral of I, if I is a constant, TL cross B, right? TL cross B. So this is the net force acting on the net force acting on a current carrying wire in presence of external uniform magnetic field, right? In presence of external uniform magnetic field, right? Now, magnetic field here is a uniform. We have to just integrate this vector, right? So TL cross B, right? TL cross B. Now you can see here the magnetic field vector and the L vector, the effective L vector here will be between these 2 points, that will be from A to B, right? That will be called as L effective vector, right? So it is actually perpendicular to this magnetic field, right? We can write it as DL, right, multiplied by B, right? So integral of dl will be the L effective length of this L effective vector, right? Length of this L effective vector, right? That will be actually 2r, right? That will be equal to 2r, right? So the magnitude of this force vector will be nothing. It has to be along. It has to be 2s bir. This is the net magnetic force acting on a charge carrying. Net force acting on a uniform current carrying wire in presence of external magnetic field, right? So the net force is always given by on a current carrying wire because of the external magnetic field, that's I dl cross B, right? Using this integral, we can find the net magnetic field and net magnetic force. Now this B is nothing, it's the external magnetic field, right? This is nothing, this is the external magnetic field. So this is how we can find the magnetic force acting on a current carrying wire in presence of external magnetic field, right? So that's it for today. We'll be discussing the last session for this chapter, magnetism, day after tomorrow, right? So we'll stop here. Till then, take care and goodbye.